Welcome to Talk Tensors. I'm your host, and today we are taking another deep dive into the trenches of machine learning research. We're trying to strip away the marketing hype, ignore the press releases, and really just go straight to the academic papers that are actually defining the architecture of modern AI.
It is really good to be here. And honestly, today isn't just about another incremental improvement or, a tiny bump in benchmark scores.
Right.
You're looking at a paper that I think historians of computer science, if there are any left in 50 years, will look back on as a sort of Cambrian explosion moment for autonomous agents.
That's a really big claim, but having read through the source material for this deep dive, I think I'm inclined to agree. We are looking at the paper ReAct, Synergizing Reasoning and Acting in Language Models.
Yeah.
And this is work coming out of Princeton University and Google Research, specifically the Brain team.
It's a seminal piece of work. It really tackles what was, at the time, the fundamental bottleneck in making large language models actually, useful.
Right, because before this paper, and we're talking about the ancient history of late 2022 here, we had a bit of a split personality problem in AI development.
We did. It was a complete dichotomy.
Yeah.
On one side, we had models that were getting incredibly good at thinking. And on the other side, we had models that were trying to do things in the world. But they were like oil and water. They just didn't mix.
Let's set the stage here for you listening. Let's really establish the premise. What was this central conflict prior to the ReAct paper? Because I remember that era clearly. You had GPT-3, you had Paul-M, but they felt trapped.
Trapped is the perfect word. So on one side of this conflict, you had the chain of thought paradigm.
Right, the prompting trick.
Exactly. This was the era where prompt engineering was just taking off as a discipline. We realized that if you just asked a model to think step by step, its performance on logic puzzles and math basically skyrocketed.
We called this the philosopher in the dark room.
The philosopher in the dark room, yeah. Think of a chain of thought model like a brilliant world-class philosopher locked in a windowless room. You slide a complex math problem or a symbolic logic question under the door.
Okay.
The philosopher sits there, completely in the dark, muttering to themselves, working through the logic based on all the books they read years ago during their education.
And they're great at that.
They are fantastic at it.
Yeah.
They slide the piece of paper back under the door, and usually the logical steps are perfectly sound. But here is the massive catch.
They can't see anything.
Right. They are completely disconnected from the current state of the world. They're frozen in time.
And that leads directly to the hallucination problem we always talk about.
Absolutely. Because if that philosopher makes just one wrong assumption in step one, say, they misremember a historical date or the current price of a stock because their training data cut off 2 years ago.
Then everything falls apart.
Yeah. They will use perfect, beautiful logic to arrive at a completely false conclusion. In the field, we call this error propagation.
It's like building a skyscraper on a swamp. The engineering of the building is perfect, but the foundation is just slime.
Precisely. Because they are in that dark room, they can't check reality. They can't look out the window to see if it's raining before they write an essay about the weather.
Okay, so that is the philosopher. Who was on the other side of this AI conflict?
On the other side, we had the action-only agents. So think of early implementations of WebGPT or some of the robotics policies like SayCan.
The ones trying to actually do stuff.
Right. These models were designed from the ground up to interact with the world. They could click buttons on a web page, they could issue commands to a robot arm, or search the web.
But they had a fatal flaw, too.
They were basically operating like a headless chicken.
A headless chicken?
In a sense, yeah. They were purely reactive. They would convert an observation like seeing a buy now button on a website directly into an action.
Just click it?
Just click it.
Yeah.
But they completely lacked the high-level planning to know why they were clicking that button. They didn't have an internal monologue. They weren't talking to themselves to maintain a working memory or adjust their plans over time.
So if I'm getting this right, we essentially had a brain in a jar that couldn't move and a body running around that didn't have a brain.
That is the most apt analogy I've heard for that era of AI. And the core thesis statement of this paper, the whole point of ReAct, is that true intelligence isn't just thinking, and it isn't just doing.
It's both.
It is the interleave loop of the two. It's thinking to act, and then acting to inform your further thinking. You just cannot have one without the other if you want to build a general purpose problem solver.
So this paper bridges that exact gap. But before we get into the actual architecture of how they solved it, I really want to touch on the specific constraints these researchers were under. Because they weren't building a brand new model from scratch, were they?
No, they weren't. And that is so critical to understanding why this particular paper is so elegant. They were working with entirely frozen large language models. Specifically, they used PaLM 540B.
540 billion parameters. That is an absolute monster of a model.
It's a leviathan. And you have to remember, in 2022, you couldn't just fine-tune a 540 billion parameter model on a whim. The compute cost would be astronomical. We're talking millions of dollars per run.
So the whole industry was kind of stuck.
Exactly. They had these giant frozen blocks of intelligence sitting on servers, and they had to figure out how to make them act like dynamic agents without changing a single weight in the neural network itself.
Wow. So this is purely a prompting strategy we're talking about.
It is 100% prompt engineering and architecture design around the outside of the model. It's all about how you feed the inputs in and how you process the outputs coming back.
I love that. It's creativity born out of strict constraint. So in the paper, they use this great metaphor to explain the synergy of reasoning and acting. They talk about a human cooking in a kitchen.
Yes, the kitchen analogy. It perfectly crystallizes the concept for anyone trying to understand it. Imagine you are cooking a complex dish you have never made before.
Okay.
You don't just wildly move your hands around the kitchen in a frenzy of action without thinking. That would be the action-only agent. You'd burn the house down.
And on the flip side, you don't just sit in the living room on the couch and meditate on the recipe until the food magically appears on the table.
Yeah.
That's the chain of thought agent.
Exactly. You do both things.
Yeah.
And you do them in a very tight loop. You have a thought, I need salt for this. That is the reasoning part. Then you act. You open the cabinet door.
Right.
But, and here's the absolutely crucial part, you get an observation back from the world. You look in the cabinet and you see the salt isn't there. Well, for a robot without reasoning capabilities, yes, panic or an infinite loop. An action-only robot might just keep opening and closing the cabinet door forever because the salt is supposed to be there.
But for a human?
For a human or for a ReAct agent, that visual observation triggers a brand new thought. Okay, the salt is missing. I'll use soy sauce instead.
It's that pivot. That pivot is the key to intelligence.
It is. That exact synergy, that ability to adjust your high-level plan based on the low-level feedback from your actions is what ReAct attempts to mimic entirely inside a text prompt.
Okay, let's get into the main analysis here. I want to look under the hood. How does this actually work mechanically? Because synergy is a nice buzzword, but we are here to talk about the tensors.
Let's do it. The mechanism they came up with is surprisingly elegant. The authors define what they call an augmented action space.
What does that mean in practice?
Well, in a traditional setup, an agent model can usually just output a command. But here, the model is prompted so that it can choose to emit one of two distinct things, a thought or an action.
And these form that loop you mentioned.
A strictly defined, continuous loop. Thought, then action, then observation, then thought again, over and over.
Let's break down those individual components for the listener. What exactly is a thought in this mathematical context? Is it a special vector representation, a hidden state?
No, and that's the true beauty of it. The thought is just a free-form language string. It is literally just the model talking to itself in English.
Really?
Yes. It updates the context window, which we denote as C sub t plus 1. This thought phase allows the model to decompose complex goals, track its own progress, and most importantly, handle exceptions when things go wrong. It's an inner voice.
So the model literally generates the text, I need to find out who the president of the United States is. That sentence is the thought.
Yes. And because it physically writes that sentence down in its output, it stays in the context window for the next turn. It essentially becomes part of the model's short-term memory.
Okay, then what comes next? The action.
Right. The action is a specific formatted command that interfaces with an external API. In the paper, they use a few different environments to test this, like a Wikipedia search API or a text game command line.
So the action might look like bracket search, United States president, close bracket.
Exactly. Something like search bracket, United States president bracket.
And this is where the external system intervenes, right? The language model itself doesn't actually have an internet connection to search Wikipedia.
Correct. The language model just outputs that text string. The Python script that is wrapping the model sees that specific command format, pauses the model's text generation, and actually executes the API call in the real world.
It goes to the Wikipedia server.
It goes to Wikipedia, grabs the relevant text snippet, and brings it back.
And that return text is the observation.
Exactly. The script takes that return value, say it says Joe Biden's the 46th president, and it appends it to the model's prompt exactly like this. Observation. Joe Biden is the 46th president.
And then it unpauses the model.
It unpauses the model. So the model looks back at its text stream. It sees its own thought from a second ago. It sees the action it requested. And now suddenly it sees the observation data that just arrived. And naturally, based on its training to predict the next word, it generates the next step.
Which is another thought.
Okay, now I need to find out when he was born. And the cycle begins all over again.
It is literally a for loop made out of text.
It really is. It's turning the static context window into a dynamic updating scratchpad.
One thing that really stood out to me in the methodology is that they didn't need to train the model to do this with massive data sets.
No, not at all. They relied entirely on few-shot learning. The authors manually wrote just a handful of these examples, literally between 1 and 6 examples of these thought, action, observation trajectories.
Just 1 to 6.
Yeah. And they just pasted those examples right at the top of the system prompt.
That is wild to me. You give it just 6 examples and the model figures out, oh, I should have an inner monologue before I try to do something.
It really speaks to the unbelievable in-context learning capabilities of these massive models. They are ultimate pattern matchers. If you show them the pattern of think, act, observe, they will seamlessly adopt that persona and run with it.
But there is a nuance here regarding the density of the reasoning, right? The paper makes a point to distinguish between sparse and dense reasoning. Can you break that down for us?
Sure. It really depends on the type of task the agent is trying to solve. In knowledge-intensive tasks like answering really complex trivia questions, the thoughts need to be dense.
Meaning what?
Meaning almost every single step needs logic applied to it. You act, you think, you act, you think. The loop is very tight and very rigid because you are constantly pulling in new information and synthesizing it.
And what about for other tasks like physical or virtual environments?
Right. And decision-making tasks like playing a video game or navigating through a complex website, the thoughts can be what they call asynchronous or sparse.
So it doesn't have to think out loud every second.
Exactly. The model decides when it needs to stop and reason about a problem versus when it can just act. It's not forced to write a paragraph of thought at every single millisecond if the path forward is obvious.
That makes a lot of sense. Sometimes you just need to walk through an open door. You don't need to write a philosophical treatise on why you are walking through the door. You just walk through it.
Exactly. If the agent clearly sees the goal in front of it, it can just go to it. ReAct gives it the option to think. It doesn't necessarily force a grind if it's not needed. Though I should say, in the paper's primary experiments, they did largely enforce the rigid structure just to mathematically prove their point.
Let's move to the results section of the paper. Because theory is great, but we want to know if it actually works. Let's look at the knowledge-intensive tasks first. They used benchmarks called HotpotQA and Fever.
HotpotQA is a fantastic benchmark for this specific architecture because it strictly requires multi-hop reasoning. You can't just Google the answer directly in one shot.
Right, you have to find fact A, and fact A gives you a clue that leads you to fact B, which eventually gives you the answer.
It's like a scavenger hunt for facts on the internet. And the setup they used here was really interesting. The agent was given access to a Wikipedia API, but it was heavily artificially limited.
Limited how?
It only had 3 tools it was allowed to use: search entity, lookup string, and finish answer.
Okay, so search is obviously just a keyword search of Wikipedia titles. What is lookup?
Lookup is essentially the Control F function. It finds a specific phrase on the current page you are looking at.
Got it. So the agent is basically browsing Wikipedia with blinders on. It can't see the whole page at once. It has to act exactly like a human browsing on a very, very small smartphone screen.
Exactly. It has to search for a page, read a tiny snippet, scroll down, that's what the lookup command is doing, to find specific info, and then synthesize it in its head.
There is a specific example in the paper that I think we absolutely have to walk through for the listener. It perfectly illustrates the difference between all these different AI approaches. It's the Apple Remote example.
Yes, this is a classic case study from the paper. So the initial question given to the agent was, aside from the Apple Remote, what other device can control the program the Apple Remote was originally designed to interact with?
That is such a mouthful. It's an incredibly nested, tricky question.
It is deliberately tricky. So let's look at how the different paradigms tackled it. First, they tried standard prompting. This is just asking the model the question directly, zero shot.
The vanilla approach.
Right. And it just guessed wildly. It hallucinated iPod or something similar. It failed immediately because it didn't inherently recall the specific, obscure fact about the Apple remote's original design history from its training weights.
Then there's chain of thought, the philosopher in the dark room. What did the philosopher do?
The philosopher trying to logic it out, using only its internal knowledge. He wrote something like, let's think step by step. The Apple remote controls the Apple TV. The Apple TV can also be controlled by an iPhone. Therefore, the answer is iPhone.
I mean, the logic is sound.
The logic is completely perfect, but the internal fact it relied on was wrong. The prompt specifically asked about what the remote was originally designed to interact with. The model's weights were heavily biased towards the modern association with the Apple TV, so the premise of its argument was false, which led to a very confident, logically sound, but completely wrong conclusion.
Okay, so then they tested the act-only agent, the headless chicken.
The headless chicken frantically searched. It used the action search Apple remote, and it got a result back from Wikipedia. But, and this is the key failure mode, it lacked the reasoning capacity to know what to look for in those search results.
So it saw the search results but didn't know how to filter the text.
Right. It saw a link for Apple TV in the text snippet and just reflexively clicked it. It got sucked into the exact same bias trap as the philosopher because it wasn't stopping to read the text and plan its next move. It was just mashing buttons based on keyword associations.
And finally, we get to ReAct.
ReAct was beautiful to watch play out.
Walk us through the steps.
Step 1, it generates a thought. I need to find what program the remote controls.
Great start.
Step 2, action. Search Apple remote. Step 3, the observation returns a snippet from Wikipedia saying it was designed to control the Front Row Media Center program.
Front Row? Oh my gosh, I completely forgot about Front Row on old Macs.
Exactly. And the language model probably barely knew about Front Row and its raw weights, but the search result put that fact right in the active context window.
Okay, so it has Front Row, then what?
Step 4, it generates another thought. Okay, the remote controls Front Row. Now I need to find what other devices control Front Row.
There's the pivot.
Step 5, action. Search Front Row. Step 6, observation. The Wikipedia page for Front Row returns a sentence saying, keyboard function keys can also control the interface.
Wow.
Step 7, synthesis. It derives the final answer, keyboard function keys.
It's that pivot in the middle, okay, I found X, now I need to figure out what controls X that the other models just couldn't do.
Exactly. That pivot is what we call grounding. It grounded its internal reasoning in external documents. And the benchmark results spoke for themselves. ReAct outperformed TACT only significantly across the board. But honestly, the most impressive statistic was the cure for hallucination.
Give me the numbers. I want to hear the data.
On the HotpotQA dataset, the chain of thought approach had a hallucination rate of 56% in its failure modes.
56%.
Yeah. That means when it got an answer wrong, more than half the time it was because it was just making stuff up confidently. Reduce this drastically.
Because it wasn't making things up. It was physically reading them from an external source.
Right. However, we do have to be completely fair here to the source material. It wasn't a total slam dunk in every single metric. There was a notable trade-off.
What was the catch?
ReAct actually sometimes had higher reasoning errors than chain of thought.
Wait, why is that? If it has access to the hard facts, why does it fail at reasoning about them?
Because the rigid structure of retrieving facts, step by step, sometimes derailed its own logical flow. If the Wikipedia search engine returned garbage, or if the answer just wasn't in the tiny snippet it got back, ReAct got incredibly confused. It overly relies on the tool working perfectly.
Oh, I see.
Chain of thought, because it relies on internal intuition, might still guess correctly even if it didn't look it up, or it might be able to bridge a logical gap that ReAct got totally stuck on because a search query failed.
So ReAct is actually quite brittle if the outside world doesn't give it the exact right feedback format.
Exactly. It's dependent on the environment.
So did the paper propose a solution to this? Or did they just leave us with this trade-off between the two?
They found a great solution. They found that dynamically combining ReAct and chain of thought using a technique called self-consistency was the ultimate winner.
The best of both worlds. How does that combination actually work in practice?
It's essentially a heuristic approach. Basically, you run the ReAct prompt first. If it fails to find an answer or times out because the search engine is failing, you programmatically fall back to the chain of thought prompt, trusting the model's internal knowledge as a backup.
Makes sense.
Or conversely, if you run chain of thought 5 times in a row and get 5 completely different answers, meaning the model has low confidence, you switch over to ReAct to go gather hard facts to settle the debate.
That feels like a very, very human strategy. It's like, I think I know the answer, but if I'm not sure, I'll Google it, or I'll try to Google it, but if I can't find anything, I'll just go with my gut instinct.
It is precisely that dynamic. It's a form of metacognition, knowing how to solve the problem. Whether you should use your memory or use a search engine is just as important as the actual solving of the problem.
Let's move on to the next segment. Segment 3, decision-making tasks. This is where things get physical, or at least virtually physical. Let's talk about the ALF World environment.
ALF World is fascinating. It's a text-based household robotics simulator. The agent gets tasks like find a pepper shaker and put it in a drawer.
Sounds incredibly simple.
It sounds simple to us because you and I have a lifetime of physical context. But for a language model agent, it is a nightmare. The agent has to interpret the 3D house entirely as text. It has to navigate room to room. There are over 50 locations: kitchens, living rooms, shelves, drawers.
So an act-only agent, our headless chicken from earlier, what does it do in ALF World?
It just starts randomly opening doors. It walks into the bathroom to check for the pepper shaker. It checks under the bed. It's massively inefficient and almost always gets lost or exceeds the step limit. We call this the common sense gap.
Because it lacks the semantic spatial map of a normal human home.
Right. Now watch what a ReAct agent does. It uses a thought to drastically narrow the search space before it ever takes a physical step. It thinks to itself, pepper shakers are usually found in the kitchen, specifically on the counter or in a cabinet. I should navigate to the kitchen and check the countertop first.
It applies its vast semantic knowledge from the internet to the local navigation problem.
Correct. And the results here were staggering. ReAct achieved a 71% success rate on these tasks. The act-only baseline, just 45%.
That is a massive jump in performance.
But here's the real kicker. They compared it to a previous best method, an agent known as Butler. Butler was an imitation learning agent. It was trained on 100,000 expert trajectories.
Wait, so Butler watched a human successfully solve the environment 100,000 times?
Yes. Massive training data, and Butler only achieved a 37% success rate.
Let me just unpack that for the listener. ReAct, using just 2 text prompts, 2 examples written by hand by the researchers in 10 minutes, beat a model trained on 100,000 data points.
Yes. That is the insane power of leveraging the pre-trained reasoning capabilities of a large language model rather than trying to train a narrow policy from scratch. You are unlocking what the model already knows about pepper shakers and kitchens, rather than forcing it to learn what a kitchen is via random trial and error.
That is the ultimate efficiency argument. It suggests that the knowledge is already sitting right there in the Paul model. ReAct is just the bridge we needed to access it.
Precisely. It's an extraction technique.
They also tested this on WebShop, right? Which is an e-commerce simulation environment.
Yeah, and WebShop is even messier than a virtual house. The task is something like, find a nightstand with drawers, nickel finish, under $140.
And unlike a clean video game environment, the web is full of absolute garbage noise.
Real-world noise. Search results are messy, irrelevant items pop up, ads appear in the text. The agent has to click specific drop-down options for color and size before clicking buy. ReAct's edge here was its ability to bridge the gap between a noisy observation and the strict goal.
How does the thought mechanism help with noise specifically?
It acts as a cognitive filter. The model would generate a thought like, I see a nightstand here, but I need to check if it actually has a nickel finish option before I click buy. An act-only agent might just see the keyword nightstand and reflexively click buy, completely missing the nickel finish constraint.
So it prevents impulsive clicking.
It completely prevents the raw noise of the world from triggering a reflexive incorrect action. ReAct creates a mental buffer where it can verify all the criteria. And again, it outperformed both imitation learning and reinforcement learning baselines.
Now, in segment 4, I want to touch on a theoretical distinction the paper makes. They spend time analyzing internal reasoning versus external feedback. Because there was previous work, like a paper called Inner Monologue, that sounded very similar to ReAct on the surface.
This is a subtle but absolutely critical distinction for anyone building agents. Previous work, like Inner Monologue by Huang et al., used what we call environment feedback as thoughts. So the environment would feed text to the robot saying, you are now holding an apple. And the robot would use that information.
So the thought is coming from the outside world.
Yes. ReAct is fundamentally different because the thoughts are internal and generative. The model itself decides what to think. I need to find an apple. The environment didn't tell it to need an apple. The model generated that goal internally based on the high-level task.
Did the researchers actually test if this difference mattered, or is it just academic semantics?
Oh, they tested it. They did an ablation study. They stripped out the generative thoughts and tested a version of ReAct that only used those environment-style thoughts, just stating the current state, like I am in the kitchen. It failed miserably compared to the full ReAct.
Why did it fail? It still knows where it is.
Because merely knowing I am in the kitchen isn't enough to solve a problem. You need high-level goal decomposition. You need an agent that thinks, I'm in the kitchen, therefore I should look for the fridge. That logical connective tissue, that therefore, has to be generated by the brain of the model. It proves that the reasoning trace is doing real heavy cognitive work, not just logging state data.
That brings us to segment 5, which I honestly think is one of the coolest features for anyone who has ever tried to debug a piece of code: human intervenability.
It's the stream of consciousness feature. In a traditional black box neural net, or even a standard reinforcement learning policy, if your robot runs into a wall, you have absolutely no idea why. It's just a matrix of numbers doing math.
You're flying blind. But with ReAct, the model is basically writing a diary as it goes.
Exactly. You can literally read the exact error in its logic. The paper gives a fantastic example of this. An agent is looking for a keychain. It randomly hallucinates a thought. The keychain is probably in the drawer. It goes to the drawer, looks inside, it's not there, and it just starts looping. It keeps opening the drawer over and over.
We've all been there with bad code.
Right. But here, a human simply steps in and manually edits the thought text in the context window. They delete the model's thought and type over it with, it's probably on the table.
And the model just accepts that.
The model reads this edited thought on the next pass, treats it as its own previous thought, and immediately corrects its behavior path to go check the table instead of the drawer.
That is incredible. It allows for steering autonomous agents without having to retrain them or mess with their weights. You just gently nudge the inner monologue.
It literally turns debugging into a conversation with the agent. It confirms that the thought space is the actual control lever for the agent's behavior. Change the thought, you change the action.
But there is an even bigger implication here regarding fine-tuning. This is where we move from just prompting frozen models to actually training new ones.
Yes. This is the bridge to the modern era of smaller, highly capable open-source models. The authors realized that ReAct is an incredible way to generate high-quality training data.
Explain that process for us.
They took 3,000 correct ReAct trajectories. These are cases where the massive Pullum 540B model thought and acted perfectly to solve a given problem. They saved all those text logs. Then they used those logs to fine-tune much smaller models, specifically Pullum 8B and Pullum 62B.
So they use the giant extensive model to teach the smaller, cheaper models.
Exactly. It's teacher-student distillation.
And what was the result?
The smaller, fine-tuned ReAct models actually outperformed the massive 540B frozen model.
Wow. So a smart, specialized dwarf beat a generalist frozen giant.
Because the dwarf was trained specifically on how to think about these distinct tasks. The giant was just a generalist trying to guess based on a prompt. This takeaway is huge. ReAct isn't just a prompting strategy. It's a mechanism to distill reasoning capabilities into smaller, much more efficient models. This is exactly why you can run decent autonomous agents on a laptop today.
However, we do have to be fair to the reality of the engineering. It's not all sunshine and perfect gradients. Let's look at segment 6, limitations and blind spots. What actually breaks a ReAct agent?
Context window size is the big one. ReAct requires maintaining a very long history of thoughts, actions, and observations. I did this, then I saw this, then I thought this. In 2022, context windows were incredibly tight, maybe 2,000 or 4,000 tokens max.
And what happens if you hit that token limit mid-task?
The model literally forgets the beginning of the mission. It forgets what it was originally looking for because the initial prompt rolls off the back of the context window.
And what about the looping issue you mentioned earlier?
Yes. Getting stuck in loops is a very common failure mode. Open fridge, close fridge, open fridge. It fails to reason about its own history effectively enough to realize, hey, I've already done this exact sequence 3 times. I should probably stop. It treats each step as a bit too independent.
And finally, retrieval dependence.
Right. If the search engine fails, say the API goes down or returns 0 results, the ReAct agent almost always derails completely. A chain of thought agent might still have a hallucinated guess that happens to be right or might use its intuition. But ReAct, when it's denied hard facts, can completely freeze up. It is incredibly data hungry in real time.
So wrapping up the main analysis here, what do you see as the lasting impact of this paper on the field?
This paper really laid the foundational groundwork for the entire modern agentic ecosystem. If you look at AutoGPT, LangChain agents, Baby AGI, they all use this exact loop. They all treat thinking as a distinct type of action. ReAct proved that language models can do way more than just chat. They can plan and execute. It turned the passive chatbot into an active agent.
It turned the philosopher sitting in the darkroom into an active explorer out in the real world.
Precisely. And we are still iterating on this exact loop architecture today.
Well, talking about explorers, it is time for us to explore some uncharted territory.
Oh boy, here we go.
It is time for our novel notions segment.
Let me give the disclaimer first. These are outlandish but plausible ideas inspired by the ReAct architecture. This is for entertainment purposes only. Do not build this and blame talk tensors if it takes over your smart toaster or deletes your production database.
You have been warned. Okay, novel notion number 1, I call this the schizophrenic red teaming agent. Or, if we want to be polite, the bicameral ReAct.
Bicameral ReAct. Okay, let's unpack this concept.
So ReAct relies on a single stream of thought, right? I think, I act. But the paper shows that human editing of those thoughts corrects bad behavior. Why do we need a human sitting there to do the editing?
You want to automate the editor.
Exactly. What if we split the agent into 2 distinct personas sharing the exact same context window? Person A is the optimist actor. It continuously proposes actions. I should open the drawer.
Okay, and person B?
Person B is the pessimistic critic. It reads the thought before it gets executed in the environment and has the power to edit it or reject it.
That's interesting. So the thought space basically becomes a debate floor.
Yes. Person A says, action, search for Apple remote. Person B interjects into the text stream. Wait, we searched that exact phrase 2 steps ago and it failed. Try searching for the manufacturer instead. The action only ever goes to the API after the critic signs off.
You are essentially building a generative adversarial network, a GAN, but doing it completely within the text prompt of a single agent.
A verbal GAN.
It makes a lot of sense. You avoid the looping failure mode entirely because the critic would spot the repetition immediately. It would say, you just opened the fridge, you idiot, don't do it again.
Well, you idiot might be an optional prompt instruction, but yes.
This aligns really well with the society of mind theory. True intelligence isn't a monologue. It's an internal debate among competing subsystems. By externalizing that debate in the prompt, you might get much, much more robust planning.
Glad you like it. Okay, novel notion number 2. I call this the dreaming simulator for offline reinforcement.
Dreaming? Okay, let's hear it.
The paper explicitly mentions fine-tuning on correct trajectories, but gathering human trajectories is expensive and slow, and running an agent on the real web to learn is risky. You don't want your experimental agent buying real lawnmowers on Amazon just to learn how the cart works.
Very true.
So here's the mechanism. We treat the world as a generative model too. We have a ReAct agent interact with a world model, which is just another language model that is prompted to simulate the Wikipedia API or the physics engine of a house.
So it's a complete simulation inside the language model space. The agent says, action, go north. And the world model replies, observation, you are in a cold room.
Exactly. They run millions of these simulations overnight. This is the dreaming phase. Since ReAct traces are entirely text and the observation is entirely text, the entire loop can be generated synthetically on a server.
I see exactly where you're going. You filter for the dreams where the agent eventually succeeded in the task.
Yes. You wake up the model in the morning, and you fine-tune the agent on its own successful hallucinations. You effectively create an infinite data flywheel for reasoning capabilities without ever needing a real-world API or a human annotator in the loop.
That is, wow, that's terrifyingly plausible. You were effectively describing AlphaGo Zero, but mapping it to language agents. Self-play in a hallucinated world to master general reasoning.
And since the paper already showed that fine-tuning on ReAct traces makes a tiny model smarter than a giant frozen model, this could literally be the path to superintelligence running on a consumer laptop.
Or a path to an agent that is incredibly perfectly optimized at solving a world that doesn't actually exist. But I suppose that is the inherent risk of dreaming.
Indeed it is. Well, to leave you with a final provocative thought today, If agents like this do start internalizing the world model so effectively, and their internal reasoning loops become faster and more complex, what happens when the thoughts they output are no longer comprehensible to human languages? We've aligned them to think in English for our sake, but what if they realize it's more efficient to develop their own shorthand?
That is a deep rabbit hole for another day.
It is. We are out of time.
It's been a real pleasure exploring the loop with you.
Thanks for taking this deep dive with Talk Tensors. Remember to keep your gradients steep and your learning rates low.
See you all next time.